All right, you can get started.
Okay, just something just popped up on my screen and I'm gonna fix it. Oh, how did I have this? Okay, sorry, gotta kind of reset my screen here. I have it so that I'm reading my text, but my text just got really small and I can't read it anymore. Um, and it's not letting me move it. No, okay. Yeah, you move and then
It can be your notes. I mean, the head of the board. Like,
okay, yeah, whatever. This no, that was okay. I'm trying to there we go. Wonderful. Was trying to make the notes full screen, but all the Zoom toolbars were hiding the button to do that. Okay. Um okay, thanks for coming back. Uh and I'm about to be ready. Okay, so let me remind you where we were yesterday. So we're in the middle of a fairly unpleasant lemma, but where this is going, so the goal is really prove the most unpleasant but really useful facts about dimension in a strongly minimal structure. Um, and then just use it over and over and over again to prove a whole bunch of nice things. So we're kind of trying to push through the hard parts. And so where we are is we've got a strongly minimal structure M. Where did I write that? Quite a while ago. So we have a strongly minimal structure M, and to remind you, that means that the theory of M is strongly minimal. I think I should have said that more explicitly last time. So if I say M is a strongly minimal structure, that means the theory of M is strongly minimal. Um, but we're not assuming that M is like a particularly big model or anything like that. It's just any model. And we've defined dimension, and we're trying to prove now something called, which I have called the M cutting lemma. And the M cutting lemma says if you have x inside m to the m times m to the n, you can compute the dimension of x by doing a bunch of separate computations in m to the m and m to the n. So you can cut it between the m and the n and just do the dimensions on the left and on the right. Precisely by this formula, dimension of x here is the maximum of I plus the dimension of I wrote that wrong. Xm of I, where Xm of I is the set of points that have I dimensional fibers. Right? So we're just saying that if you have like seven dimensionally many points and all of those seven dimensionally many points have three-dimensional fibers, then you'd expect a total dimension of seven plus three. We're just saying that that works. Okay? And we're proving it by induction. And
wait, did something just happen with the sound? And also, are your notes aren't changing. I mean, the board is not changing.
no, I'm about to scroll to new stuff.
Oh, okay.
Okay. Does it sound okay? Can you hear me?
Sound keeps coming out, but it's still on. It's coming through there. Yeah. It's like a problem on our end because it's coming through the laptop.
Okay. I mean, if there's, tell me what you want me to do. Should I just keep going or?
We're hearing this somehow, but it's really weak. It's coming from like a different speaker.
You should keep talking about it for a little while so we identify where it's sounding.
Should I? I can't hear everyone that well. Am I supposed to keep going or am I supposed to
Is this
wait?
thing like turned off or something? No, this is.
I'm gonna wait.
What were you gonna say before the comment out?
No, I was like, we can now see the change of whatever.
But like the notes weren't changing.
Yeah.
Yeah, I was gonna say the same thing and then the sound cut out.
See here. Can you speak a little?
Ben, could you just talk continuously?
Okay. Hello. Yeah, okay. Is this good?
What are we?
I can I'm scrolling right now. Does it look like I'm scrolling?
It doesn't show it's scrolling
No?
either.
Oh, okay. Well, yeah, so okay, so I was back on this lemma statement the whole time, and it looks like I can't really see that well, but it looks like I was that on your screen it's not back on that lemma statement. So yeah.
the sound right now is coming out of the projector. Also, so you said you scrolled, right? We don't see anything changing on your shared screen.
Yeah, I'm moving it constantly.
Yeah, it's nothing is changing on that. Maybe could you try like stop sharing and then share?
Yeah,
like,
yeah.
message
Oh,
everybody,
wait.
make it
Oh,
like-
okay. Actually, wait, why does this? Yeah, okay. Weird. Okay.
There we go. Everyone missed it. Right now, there's like a laser projector in the top of the room on the ceiling, and like the sound is coming out of like a tiny speaker on that for some reason.
Okay, I can
basically hear it, but it just it's
I
sort of
see
quiet.
it. I see it's moving now.
But yeah, now it's moving.
But you're saying that the speaker that everyone is hearing me from is not good? Is that the
It's not
problem?
the best, but we can hear.
Okay.
I don't think we have any.
Yeah,
Other
the problem
speaker.
with this device here in the class. Just
Yeah.
another one.
So I think you can. Okay.
Yeah.
Whatever. Okay, we're gonna get started again, I guess.
Okay. Oh, but now it's not moving again. I can see a little bit and I can tell it's not moving. I'm moving the screen again, so something's going on.
Oh, it moved again.
Oh, wait, so it moves now? Oh, that's
Yeah.
it's okay, so it doesn't want me to zoom in on my text. It wants me to leave the okay. It's okay. I can deal with that. So the visual thing I can deal with now. So are you trying to work on the sound thing still, or should I just keep going?
We gave up on the sound. Just keep going.
Okay.
We can hear you. It's just like it's like if you were
Okay.
like nails for feeling or something. I don't know.
Okay. All right, I'll keep going. So let me go back to the actual lemma statement because that wasn't visible. So here it is. So M is a strongly minimal structure, and I've got a definable set X in M to the M times M to the N, and I'm trying to say you can compute the dimension of X by cutting it between the M and the N and computing dimensions in X to the M, or in M to the M and M to the N, specifically by the formula. It's the max, so it's this underlined thing, the max of I plus the dimension of XM of I, where XM of I is the points that have I dimensional fibers, which again, what that's saying is that if you have, so for instance, if you have a 7-dimensional set of points that all have 3-dimensional fibers, then you have like a 7 plus 3 and you expect 10 for your total dimension, right? And we're just saying that you can do all computations like that and max them all, and then you get the correct dimension of X. Okay. Again, it's not a pleasant proof, but you kind of do it once and then it's extremely useful and everything else will be better. So the proof, it's by induction on N, which is how many things are on the right side of the cut. And we did the first inequality. So I'm doing it by the left and right inequalities. The less than or equal to inequality was done yesterday. And that's the one that says that one of the I components has to realize at least the dimension of X. So that's saying that if you break X into the I parts, then one of the I parts has to realize the full thing. And now we'll do the easier part. This is a bit easier, which is the fact that each of the I parts by itself has dimension at most the dimension of X. Right? So now we'll do this. And what this means, i.e. what this means is that the dimension of X is at least as big as I plus dimension of XM of I for all I. And I hope that that's a very intuitive statement. So what that's saying is just, okay, so it's saying here's the set XM of I inside of the M to the M. And then if each fiber coming off of here has precisely dimension I, then the total dimension of this piece is just, well, the left part plus I, right? So you just, let's say this part here is D, then you just get D plus I. So you have a d-dimensional set with i-dimensional pieces coming off of it, then you get d plus I. That's all it's saying. Okay, so let's just write it down. So we fix I, and here remember I is going to be between negative infinity and 0, etc. up through n, because it represents the dimension in m to the n. And we can assume that I is not negative infinity because, well, if I was negative infinity, then you'd be saying that something, that the lower part, the thing we want to be small in the inequality is negative infinity, and that's like certainly small enough, right? So we can pretend I is not negative infinity. Oh, sorry, negative infinity. And in particular, what that really means is we can pretend that X is not the empty set. Okay. So we can assume that X is not the empty set. Okay. So here's what we do is, okay, we follow this picture I drew. So you have this set X M of I, and then each of the points has an I-dimensional fiber coming off of it. So if Y is in this set, so if Y is in xm of I, then the fiber has dimension I, and there's got to be some reason that it has dimension I. So remember, we're in the inductive step where we have, oh, I'm sorry, I'm sorry. I lied in the sense that we're actually doing an n plus 1 now, which is a proof by induction, and we're on n plus 1, not n. Surely I said that somewhere, but this is a long proof, so it was way before. Here, there's the picture. You have m to the m, and then there's the m to the n times n. So I could go up to n plus 1, and now we want to reduce down to n. Okay, so if the dimension of xy is I, there's some reason, so there is some e, which is now in negative infinity 0, 1, such that this I is realized by e plus the dimension of x, y of e. Okay, so I'm just saying every point that has, if it has an I-dimensional fiber, then inductively there's some reason it had an I-dimensional fiber, which is coming from some e. Now, the same trick that we've done several times, there's finitely many values of e, and one of those values of e then has to happen on a big set. Right, so there is some e happens on a whole dimensional set inside this xm of I. Okay, so what that lets us do is that now we fix some set y. So I'll say y, which is inside of xm of I. It's definable. And it's got the same dimension. So the dimension of y is dimension of xm of I. And if y is in y, then I is e plus xy of e for some fixed e. So now e is fixed. So what I've done is I've just reduced the set y to something. I've reduced the set xm of I to something smaller, and now because I did that, I can assume e is fixed. Now notice that we can assume, so we know e is not 0. Sorry, e is not negative infinity because I is not negative infinity. So if e was negative infinity, then this I would be negative infinity because I is e plus something. So we can rewrite. So rewrite as the dimension of this set xy of e is just I minus e. Okay, so you can subtract e. Okay, Now, again, I know this is boring, but it's just about done. So now take Z to be just all of the points lying above Y. So be the union, be the union, be not the union, just the set of points above Y, set of points above Y. So just anything that projects into the set Y. And now, well, what do we know? So then the dimension of Z of E, okay, how do I know this? Is at least dimension of Y plus I minus E. Okay, where is that coming from? So you have the set Y, and each thing from Y extends to a bigger set, and the extensions are all I minus E, and then each point in that set extends by E. Okay, so you have whatever the dimension of Y is, every point in Y has an I minus E dimensional extension to some set here. This thing is now Z of E, and then everything there extends E. Yeah. Actually, this is not exactly Z of E. This is contained in Z of E. So because every point in this sort of left two pieces of the picture has an E-dimensional fiber, the whole thing is contained in Z of E. And well, what does this left side look like? It looks like Y extended by I minus E everywhere. And by the inductive step, we know what the dimension of that is. That's dimension of Y plus I minus E. Okay, so yeah, so Z of E contains this circle here, which has dimension this thing. Okay, sorry. And so now that tells us about the dimension of Z. So dimension of Z, well, one of the components that went into the computation of the dimension of Z inductively would be this one, so E plus dimension of Z of E. Okay, we now know something about that, so that's at least E plus dimension of Y plus I minus E, and now the E's cancel, and that's I plus dimension of Y, and the whole time dimension of Y was chosen so that was the dimension of xm of I. Okay, so dimension of Z is at least dimension of xm of I, but Z is a subset of X, so of course the dimension of X is bigger. We proved that yesterday, so dimension of X is now at least that as well. Okay, and we're done.
Recording in progress.
So any questions about that? I know that was it's that particular lemma is a bit of a mess. But you know, at the end of the day, you write it down and it sort of just every step is what it has to be. It's just kind of a long thing to keep track of. Or okay. So I'm gonna go on. I mean, yell at me if there's any questions. So now we're done with the unpleasant lemma. Let's start applying it. So now we're gonna do a much more pleasant proof. Okay, so why do we care about M cutting? Well, it immediately gives us something that I've said we're working toward. So now we can prove, I'll call this a theorem. This is permutation invariance. So if X is definable in M to the N, and you permute the coordinates, so sigma is in a symmetric group of 1 through N, then the dimension is unchanged. So dimension of sigma of X, which is just plug permute the coordinates within X according to sigma, is the same as dimension of X. Okay, so in other words, So the slogan here is that the definition of dimension, so when we define dimension, and it had this unpleasant feature that you have to order the coordinates in a specific way. In the end, you didn't have to order the coordinates in a specific way. So when we define dimension, we can order the coordinates however we want. And so in any order, in any way. Yeah, so that's what it means. Okay. So let's prove this. Okay. So the first thing, so there's like three main steps here. So the first thing, so step one is, so we may assume a particular form for sigma. So we may assume sigma is just a switch of two things I plus 1 for some I. Okay, why is this? Well, maybe you know this fact that all of the permutations of 1 through n are generated by things of that form. So why? Because the symmetric group of 1 through n is generated by those. So if you take an arbitrary permutation, you write it as a product of a bunch of switches I plus 1, and then you just start plugging in x over and over and over again successively into that all the permutations in that product. If it's going to change dimensions at some point, it has to change dimensions at some point, right? If it changes dimensions by the end, there's a first place where the dimension changes, and in that step, you would have had a switch in dimension from an I plus 1. Right? So we'll assume from now on that it's just a switch of two consecutive things. Okay. Step 2. Oh, and yeah. Okay. Let me. I can't tell if there's a question sometimes. Let me know. Step 2. We may assume n equals 2. So we're working in m to the n. We may assume n equals 2. That's a huge reduction, right? Because I mean, working with permutations in n variables is like horrible, right? But now I'm just saying you only have to switch two things. This is why we have this m cutting lemma. So why? Well, certainly n is at least 2 because we're assuming that something actually switches. If n was 0 or 1, then there's no non-trivial permutations, so we don't have to worry about that. So why? Well, we have sigma is I plus 1. If we draw this picture, if we have, say, break m to the n into, well, m to the I minus 1 times m squared, where here this is the two things that are getting switched. This is I and I plus 1 times m to the n minus I plus 1. Then what you can do is use this m cutting lemma to chop right here and write the whole thing in terms of computations on the right and computations on the left. Right? Well, computations on the right are not going to change because we're not changing those coordinates. So we can disregard. So disregard this side. And now we reduce to just m to the I minus 1 times m squared. Okay, well, now we can do the same thing. We chop it right here. Okay, and again, it reduces the computations on the left and the right, and the I minus 1 doesn't matter anymore because that doesn't change. So we disregard here. Okay, so precisely, precisely, by m cutting for m equals, what would that be, I plus 1? We may reduce to the case that n is just I plus 1. Okay. And well, okay, if you want the details, okay, so precisely what is going on here is we're saying that if you cut at n equals I plus 1, then those sets x sub m of I, or so now I is fixed, so we'll call them x sub m of j. The dimensions of those, the j is not going to change. So whether a point in up to I plus 1 belongs to the j set or the j plus 1 set or the j plus 2 set, that doesn't change. So you're taking the same collection of points and then you're just flipping the two things. And the only thing that matters is if it doesn't change under the flip. So we reduce to n equals I plus 1, and then now we do it again. So then by m cutting for this time, m equals I minus 1. Okay. And now, yeah, okay. I minus 1. Now what's going on is that the sets x m of j are not changing. Right? That's what's saying. So right. We reduce to the case n equals 2. Okay, I hope questions about this, I hope it's clear. We're just saying that we're doing computations in two separate powers of m, and in each case, one of the powers of m is not being affected at all, so we just delete it. Okay. Right, so now that's step 2, and now we assume that n equals 2. So now step 3 is we do the case n equals 2. Okay, in which case, of course, we can assume sigma is just the switch of the two coordinates. So we're just switching the two coordinates in m squared. Okay, and again, so what we want to do is we just want to take x and m squared and say if you flip the role of the two coordinates, the dimension doesn't change. So how do we do that? So we will give a coordinate invariant. So it doesn't change if you switch the coordinates. A coordinate invariant characterization of the condition dimension of x equals d for each d. So the possible d's here are negative infinity, 0, 1, 2. Because now we're in n equals 2. So for each of the possible dimensions, I'm going to write a new characterization of that dimension, right? And it's going to be clearly it doesn't matter which way you order the coordinates. So it's going to be coordinate free. And that'll finish the proof. Okay, so let's do them. So, well, the first one is easy. So if d is negative infinity, the coordinate free characterization is, well, dimension of x equals negative infinity if and only if x is empty. That's coordinate free. This, by the way, this was an exercise. I'm liable to forget to name an exercise that appears in the text as I'm going, and I think I did that yesterday. So that was an exercise. Dimension of x equals negative infinity is the same as x is empty. But you can see all the exercises in the text as you go. So that's done. And then similarly, it was part of the same exercise for 0. So dimension of x equals 0. Well, that's just the same as saying x is non-empty and finite. Again, that's coordinate free, and again, that's an exercise to go through the definition of dimension and check that that's true. So in general, we'll use that a lot. So a zero-dimensional set is the same as finite, non-empty. Okay, d equals 1. This is like a joke. Dimension of x equals 1 if and only if dimension of x is not negative infinity, 0, or 2. Right? That's going to be coordinate free, provided, of course, that we can do d equals 2. So if you can do 3 of the 4, you can do the last one, right? It's just the negation of the others. Okay, so now let's do d equals 2. So now we have the d equals 2. I'll just write that again. So d equals 2. Claim. So now we'll actually prove something. So claim dimension of x equals 2 if and only if x is, I'm going to give this a name. It's not, I didn't give it a name in the notes, but x is broad. Okay. And broad will mean the following. So broad means for all k and z plus, we can find two sets A and B in M, each of size k, so that the product is contained in X. Okay, so X is broad if it contains arbitrarily large finite boxes, which contains products A times B for A and B arbitrarily large. Okay, so so X is broad is a coordinate invariant condition, clearly. So if we can show the dimension of X equals 2, if and only if X is broad, then we're done. So let's do that. So, and if you should say, if you've seen this material before, this right here is the exchange lemma. So if you know what I'm talking about, maybe you do, we're skipping the exchange lemma, but this is where we prove the exchange lemma actually. So the exchange lemma is a well-known part of a different way of doing this stuff. So okay, so let's do this direction. So assume dimension of X equals 2. So what does that mean to have dimension 2? That means that cofinitely many fibers are cofinite. So cofinitely many of the sets xy, so I'll say xy is just the fiber, are cofinite. Okay, well, if cofinitely many of them are cofinite, then in particular, finitely many of them are cofinite for any finite size. So for any k, choose finitely many points, say a1 through ak, such that each fiber is cofinite. Okay? Because if you have cofinitely many available options, certainly you can find k of them. And now the intersection, so you have finitely many cofinite sets. What happens if you intersect finitely many cofinite sets? You get another cofinite set, right? Because the complement is a finite union of finite sets. The intersection of x sub ai is cofinite, right? And so contains, in particular, k points. Some distinct points, b1 through bk. And now we're done. So then if we take a1 through ak times b1 through bk, that's now contained in X. Okay, so that's that direction. So if you have cofinitely many cofinite fibers, then you can take a large finite number of cofinite fibers. Those intersect to a cofinite set, which contains a large finite set, and then you have a product of two large finite sets. Okay, and the other direction. Okay, so that's supposed to be an arrow. So now assume X is broad. So this means you can find large finite boxes. So the key observation here, this is like the less obvious direction. You want to say that if you can have large finite boxes, then the dimension of X equals 2, which is something stronger, saying you can have cofinitely many cofinite fibers. So from some big finite thing, you want cofinite things. And so this, hopefully you can see, we're going to need to use the uniform finiteness fact, right? So the fact that if things get arbitrarily big finite, then they get infinite. Okay. So by uniform finiteness, there is some k, so that for any y, so for all y, if the fiber xy has at least k points, then xy is cofinite. So that's uniform finiteness. Okay. Well, by broadness, we can take a k by k box. So take a k by k box inside X. Oh no, I don't want to do that. Okay. I don't want to take a k by k box. That's too small. So for any let's say n at least k, we can find an n by n box. Contain an x. And what does that say? So each fiber XA for A and A has size at least n because it contains B, and that's at least K, and so it's cofinite. So if you're in A, then you have a cofinite fiber. And what that means is that the set of all y such that xy is cofinite has size at least n because it contains A. Okay, so you find a big A times B box. That means that you have all the points in A have huge finite fibers, and therefore they have infinite fibers. So this is where we're using uniform finiteness. Well, now you have huge finite number of points that all have cofinite fibers, but that's true for any huge finite number, right? So in particular, now you have infinitely many points with cofinite fibers. Since n is arbitrary, okay, since n is arbitrary, that set, the set of y such that xy is cofinite, is infinite, and because it's definable, it's therefore cofinite. Okay. Is there a problem? Okay. So that means dimension of x is 2. So to have dimension 2 is to have cofinitely many cofinite fibers. Okay. Yeah, so the way this to review the way this proof works is we really only proved it in one case, right? We proved it for two-dimensional subsets of m squared. This is the only interesting case. And then every other case just follows from that. So if you can do two-dimensional subsets of m squared, then you can also do one-dimensional, zero-dimensional, negative infinity dimensional subsets of m squared, just because, you know, those are just like finite sets and non-infinite sets and whatever. And then if you can do m squared, then just by tweaking two coordinates at a time over and over again, you can do m to the n. Okay? So this is like success. We've reached the point of things are more pleasant. So, and I hope you enjoyed that proof much more than the previous proof. I think this is a fun proof. So, by the way, I should say, so this notion broad, you can extend it to n variables. So if you wanted to, I won't do this, but if you wanted to, you could say a definable subset of m to the n is broad if it contains arbitrarily large n-ary boxes, and then that'll be the same as having dimension n. You could do that by induction, but we don't need that. Okay, great. So now let's do some the corollary. Okay, so that's one thing, and now we're just going to have a whole bunch of really nice properties that just fall out of this. So now we've done the ugly properties of dimension. Now we do the really nice ones. So corollary, and I'll call this function additivity. It's because it's a preview of what will later be called additivity. I needed a different name, so I'm calling it. It involves a function in this formulation, so it's function additivity. So what function additivity says is that if you take the formula that we used for m cutting, that formula was used for a projection. to the left, right? So you're always using the projection to x to the m. M cutting is about the projection to the left m coordinates. So what we're now going to show is that you could do the same thing for any definable function. It doesn't have to be a projection. It doesn't have to be to the left m coordinates. It's just any definable function. The exact same formula works for computing dimension. So let me write it down. So let f x to y be definable. And then for each, okay, I'll put some specifics down. So let's say that x is in m to the m and y is in m to the n. And then for, we'll do a similar thing to all these inductive computations of dimension. So for e in now on the m side, so going from negative infinity to m, we'll set, I'll call it y sub f of e to be the set of y and y, so that the dimension of f inverse of y equals e. Okay, so we take the points that have e-dimensional fibers, but now it's just an arbitrary function. Then dimension of x happens to be what you'd expect. So the max of e plus dimension of y f of e. Okay, I'm gonna rewrite that smaller. Hope it fits. Okay. Dimension of x equals max of e plus dimension y f of e over all the e's. Okay. So yeah, it's the same formula, just doing it for an arbitrary function. Maybe I should point out, I think I should have emphasized this more yesterday. Take this set yf of e. We just took the dimension of it. So when we do this right here, I should say when we do this, when we say something like dimension of this set, why does that exist? Right? So this exists because dimension is definable. And that was an exercise. So I hope that's clear. You can't just randomly take the dimension of anything. You can take the dimension of a definable set. So we're in all of these statements about inductively taking dimension by maxing a bunch of things, we're using that dimension is definable. So the reason that you can take dimension of y f of e is because y f of e is a definable set, and you can take the dimension of any definable set. Okay, and y f of e is definable because if you look at the definition is saying you have the family of fibers and you're specifying which fibers in the family have a precise dimension, and that's what it means for dimension to be definable. So definability of dimension means you can pick out in a family which members have each particular dimension. And also part of that is that in a family of sets, only finitely many dimensions are going to happen. Right? And so each one happens on a definable set. Okay, so this is function additivity. Extremely useful property. We'll use it over and over. And the proof is very straightforward now. So okay, I showed you this horrible proof of the m-cutting lemma, and now I wrote a corollary that's very, very similar to the m-cutting lemma. And so you might be saying, well, no, we have to do the proof of the m-cutting lemma again. I don't want to do that. No, it's now very easy. So the proof, so let gamma be the graph. Okay, so that's the set of x, y, where f of x equals y. Okay. What's the dimension of gamma? Well, we can cut anywhere we want to, so let's cut gamma right here between the x and the y. If you're a point in x, what's the dimension of your fiber in y? Well, exactly 1 point, right? It's a function, so there's always 1 point. So the dimension of every fiber is 0. So by this will be M cutting the dimension of gamma is just the dimension of x plus 0, right? The dimension of x, just because every point in x has a 0-dimensional fiber, because the fiber is exactly one point. It's the image under the function. Okay. Now the point, what does symmetry say? So the fact that the dimension is permutation invariant, it says that we could also project to the right, to y instead. Okay, so now to be precise, we'll write it this way: let gamma prime, or maybe I'll say gamma op in y times x, just be now written backwards. So instead of yx, where f of x equals y, same set written backwards. Then, well, the dimension of gamma op equals the dimension of gamma because it's a permutation. All we did was permute the coordinates. So that's permutation invariance. And well, now let's do cutting. So now let's cut at n. So this is n cutting because we switched the m and the n. And now, what is that? Well, it's the max of, well, it's exactly what it's supposed to be. So if you do the n cutting in gamma op, what you're doing is these sets xm of I that we were considering before. It's just the sets here. It's the sets y f of e. It's exactly the same thing. It's just the set of points with each fiber. So this is the max of e plus dimension of y f of e. Because those sets y f of e are exactly the sets that show up in the cutting thing. Okay. Questions? I hope that's clear. So if that's, yeah, it's exactly the same thing. So if you write down the n cutting statement going toward y, you just, all of the fibers are precisely just the same as in the original thing. We've turned the function into a projection by taking its graph. So, okay, and that's it. So now this m cutting thing just got a whole lot stronger because now we can do it for any definable function. And now we're extra supercharged power here. So corollary, let's just infer a bunch of properties. So let's sort of summarize properties of dimension. And these are going to be new properties, so maybe I shouldn't say summarize, but it's just all things that follow out of what we just did. And I'm going to double up because I forgot to say an exercise yesterday. And so I'm just going to say a couple things that I should have said yesterday. So here's a whole bunch of properties of dimension. Okay, so dimension of m to the n is n. I never actually asked you to check that. You should check it. Dimension of the empty set is negative infinity, no matter which n you consider it to be a subset of, and the dimension of any non-empty finite set. Oh, okay. Let me write it this way. So, I'm gonna write it this way. So they're if and only if statements. So dimension of x equals negative infinity if and only if x is empty, and dimension of x equals 0 if and only if x is non-empty finite. Okay. And now some new ones. Okay, so dimension of x times y is something we can now say. What do we expect it to be? It's just dimension of x plus the dimension of y. Hope that's clear. So for instance, m to the 3 times m to the 4 is m to the 7, right? You expect it to add in a product. Why? Okay, I'm giving this as an exercise, but why? Well, you take the projection from x times y to x, right? And all the fibers have the dimension of y. So it's precisely this function additivity thing. It's like the cutting statement, but it's actually that just follows from the cutting statement. You don't even need functions, just projections. Okay. Let's say if f is definable and surjective, then dimension of f of x, okay, that's y, the dimension of y. Let me write it this way. Dimension of x is at least dimension of y. Okay, so you think of it, taking a surjective function is like quotienting by an equivalence relation. That should make it smaller, and it does. Okay, you can see that by just plug in this function additivity statement there, and it's clear. Okay, all the fibers have dimension at least 0. That's the key property. Similarly, so if f, I guess I didn't write this, but if okay, it just follows. So I won't write that. I'll just write this one. So if x is a definable bijection, then f of x, dimension of x equals dimension of y. Okay, that follows from above, because you do it 2 directions. They're less than or equal to each other, but still a useful thing. So you think of definable bijections as like equivalences, right? It's like the same set, just viewed in a different way. Those will have the same dimension, and then you can generalize this. Okay, so more generally, and this is a key notion, so I'm specifying it because we're going to use it. So more generally, say that definable sets x and y are in some fancy phrase, definable finite to finite correspondence. I often abbreviate this as just finite correspondence. But the full phrase is definable finite to finite correspondence. If there exists a definable set Z in the product with each of the projections finite to 1 and surjective. Okay, so what is this saying? This is a notion to get used to. So it's saying that almost they're indefinable bijection, but really each point corresponds to finitely many things on the other side. So it's like a definable bijection, but it's like each point is mapped to a finite set on the other side, a non-empty finite set, and vice versa. Okay, in this case, they're the same dimension. Okay, so finite to finite correspondence is preserved dimension. Okay, and again, you can do it's not crazy. You just say the proof is to say that each of dimension of x and dimension of y is the same as dimension of z. You can compute dimension of z, and you get that it's dimension of x by this additivity statement. Okay, so and I mean that we could come up with more properties, but let's stop there. So and this is all in the exercises. I basically just said sketches of the proofs, but this is all in the exercises. And now, unless if there's questions, go ahead, but otherwise we'll move on. We're on section 3 of the text still. It's the longest section, and it's just general definable sets and their properties, particularly dimension. There's one more property to talk about in section 3. So we'll do that today. I hope that we'll have time for more than that at the end of today, but we'll jump into that. So this is called stationarity. So a new topic. So new topic here, still in section 3, but the last topic of section 3 is going to be called stationarity. And So what's the idea? So I've said this before, model theory is just full of dimension notions, all sorts of dimension notions in model theory. And I said strongly minimal dimension is the best one. You can make an argument for others, but whatever. So lots of dimension notions have really nice properties. If you're familiar at all with minimality, the dimension notion there shares every property we've proved so far, except for the definition. Right. So the things we proved so far, they're wonderful, but they exist in other places. There's one property that really distinguishes strong minimality from the others, and it's stationarity. Okay, and in general model theory, what this is really saying is there's one property that distinguishes stable theories from other tame theories, and it's stationarity. So it's a similar thing. What's the idea? So note that M is strongly minimal. The same as saying that M can't be split in two. Can't be split into two one-dimensional sets. It's the same thing as M is strongly minimal. Because if you could split it into two one-dimensional sets, they would both be infinite, and they would be infinite co-infinite to violate the definition. Okay, that's the definition of stationarity. So we'd say that to let X be definable, X is stationary if X cannot be split into two definable subsets of the same dimension. So it cannot, when I say that, what I mean is it is not the disjoint union of two definable subsets of the same dimension. Okay, so of dimension dim X. That's a stationary set. You can define stationary in lots of dimension theories. The thing that will distinguish strong minimality is that they have a whole bunch of stationary sets. Okay. This is slightly different notation than other sources, by the way. I'm really defining what's called Morley degree. But when you do general stability, you use the word stationary as the analog of Morley degree. So I've always liked to say stationary because somehow it's a better adjective than always saying like degree 1 or something. So I call it stationary. All right. So that's the definition, and what's the idea? So in other words, so that is to say this another way, if we split X into some union where these are disjoint definable. So say we partition X into finitely many definable pieces. So we know from some previous lemma, the union lemma, that one of those pieces has to have the same dimension as X. And if X is stationary, it's only one of the pieces, okay? So there is a unique I with dimension of X, I equals dimension of X. Okay, and well, that is, so I'm just going to rewrite this another way. The full dimensional subset, so the dim X dimensional definable subsets of X form an ultrafilter on the definable subsets of X, on the Boolean algebra of definable subsets of X. Of X, and that is such sets form a complete type. Okay, so this is kind of the idea. This is the use of stationarity. So a stationary set is a set with a unique type built out of a unique complete type built out of the top dimensional subsets. Okay, and we call this the generic type. So we call this the generic type of X over M. And well, okay. I'm realizing that that's an exercise. So I sort of just did an exercise for you, but not really. So this is the idea. So stationary sets are sets with a unique generic type. Everything okay? Okay, it's back. All right. Okay, so let me give some properties. So just some examples. So more exercises. So exercise on stationarity. Well, which finite sets are stationary? So if oh, that's supposed to be a 1. It doesn't look anything like a 1. Okay. If X is finite, then X is stationary if and only if it's a single point. Okay, I should say, okay, I should say, in the definition, I think to be precise, we should say that X is not empty because the definition doesn't really, I mean, I'd rather not call the empty set. Okay, the empty set, if you take the definition I said, the empty set is not stationary, which is what I wanted. So that's actually fine. The empty set is the disjoint union of the empty set and the empty set. So it's not stationary. Okay. 2, m to the n is stationary for all n. So strong minimality is saying that m is stationary. And in fact, so is m to the n. So this is by induction, right? So to see that m to the n plus 1 is stationary, you suppose you break it into 2 definable pieces, and then you compute the dimensions of those 2 pieces in terms of dimensions in m to the n and m, and you use that m to the n is stationary, and so it works. Okay. So if dimension of x equals 1, then stationary is the same as really strongly minimal. So 1, then x is stationary if and only if every definable subset of x is finite or cofinite, which looks a whole lot like the definition of strong minimality. And in fact, we just call this a strongly minimal set. So X is a strongly minimal set. So we have strongly minimal structures, and then we also have strongly minimal sets. They're just sets with the same property, definable sets with the same property. And that's the same as being one-dimensional and stationary. And then, okay, let's just characterize this in one example. So suppose T is ACFP. What are the, okay, and I don't want to do arbitrary. Yeah, I think, yeah, okay, I just said in dimension 1. So P of xy is a binary polynomial, and X is the set of xy where P of x equals y. No, where P of xy equals 0. Yes. X is the set of xy where P of xy equals 0. 1 is that set stationary, so show that X is stationary. In other words, X is strongly minimal. So that's if as long as P is not the 0 polynomial, that's a one-dimensional set. So X is stationary, namely strongly minimal. If and only if that's basically an irreducible polynomial. Not quite, because it could be a power. So if and only if P equals Q to a power where Q is irreducible. Okay, so stationary is supposed to be thought of as irreducible, and in algebraic geometry, it really captures irreducible in the sense of curves. So a stationary set is irreducible in the sense that you can't break it into, you can't reduce it. Okay, well, are there other exercises? Oh yes, another exercise to add. This is important. So 2 things. Okay, then caution. Okay, caution. Before we say exercise, caution. So definability is definable. So dimension is definable, stationarity is not. So stationarity is not usually definable. So that is if we're given some family of sets, so let's say X is subset of m to the m times m to the n, then the set of y in m to the m, say where the fiber is stationary, might not be definable. So this is annoying. You have to be careful about this sometimes. So you can't just always say, here's all these stationary things are definable. The set of stationary members of a family is definable. However, it's very difficult to give an example. So, but hard to construct a counterexample. And in the exercises, I give you one. So see exercise. But it's like it's not easy. I stole it from a paper of Frashofsky, so it's not trivial. In the beginning of the class, I told you like you prove strongly you usually prove strong minimality with quantifier elimination. But I gave you a test using automorphisms instead, and I said the reason is because there's an exercise I'm going to give you later about some example where I don't know the quantifier elimination is this. Okay, so right. Oh, right. So now exercise. So even though this is not true, even though stationarity is not definable, it's got a trace of definability. So show that stationarity is preserved under elementary extensions. So if we have an elementary extension of strongly minimal structures, and you take a definable set in the smaller one, and then you look at what it becomes in the bigger one, then the one's stationary if and only if the other is. Okay. Great. So that's just some things to say. So just some exercises. Now let's move on in the material. So we want to say some things about stationary sets, and what we really want to say is that there's a lot of them. So somehow the goal is there are a lot of stationary sets in the sense that every definable set can be broken down into stationary sets. So our goal is what's called stationary decomposition. And it's like a unique factorization theorem. So every definable set decomposes into unique, in some sense, stationary components. Okay, and for example, what's that going to look like? Well, let's just take some random definable sets. So in say ACF, okay, let's say this is the plane in an algebraically closed field, and then we have say a definable set, and it's the union of say that curve and that curve, maybe plus this point, say. Okay, that is not a stationary definable set because you can break it into say the first curve I drew union the second curve I drew minus the intersection point plus the other point, something like that. So this is basically the two curves. So this has two components. We're going to say it's not stationary, but it has two stationary components, and they're basically the two curves. So that's what we want to say. So in the abstract, we want to draw that picture. Now, to draw that picture, we need a new auxiliary notion. So to make this precise, and the reason we need a new notion is we want to prove that the stationary decomposition is unique, and it's just not unique, right? So we need to refine what it means to be unique. So for instance, in this picture I drew, I could have written it as the first curve, and then the other set is the second curve together with the extra point. Or if I wanted to, I could have put the extra point in the first curve. and then the other curve by itself, right? So I have at least two ways of decomposing the set into stationary pieces, but somehow they shouldn't be seen as different because all I did was like move one point from one set to the other. So what we're going to say is that the stationary decomposition is unique up to almost equality. And for that, we need to say what almost equality is. And that's another key notion. So throughout the rest of the course, we're going to constantly use the notion of almost equality. It's like a key fact of when you have a nice dimension theory, you can talk about two things being almost equal. So let's define this. So two parts. So let x, y be definable. Let x and y say in m to the n. And should I say they're non-empty? Yeah, they're non-empty. Empty set's always weird. So two parts. So x is almost contained in y. I think this is often denoted with a square containment symbol, but I'm not going to use that. I don't think I need that. So, but what does this mean? Well, it's what you think it is. So if someone made you come up with a definition, you would get it right. You just have to think about it for a second. So x is almost contained in y if almost every point of x belongs to y. And how you can say that is if you take the points of x that don't belong to y, it should be very little. Okay, so if what we're going to do is look at the set x minus y, which is the set of points in x that are not in y, we want the dimension of that to be smaller than the dimension of x, meaning it's very little. Okay, and then two, x and y are almost equal if they're almost contained in each other. Okay, so and this is just saying like the symmetric difference. So the symmetric difference of x and y should have smaller dimension than both of them. It's another way of saying that. Okay, and so now from now on, so thus we can use language. We can say things like, I'm going to use this sort of language like almost all x and x satisfy some property. So I'm going to use language like that. And what I mean, it should be a definable property. And then I'm just saying that the set of things satisfying that property is definable. Okay. Right. So there's an exercise, by the way. I'm just going to skip it. So almost equality is an equivalence relation. That's an exercise. I'm going to say that out loud. So exercise, I'll write it down. So this is an equivalence relation. And a couple other things. So if two sets are almost equal, then they have the same dimension. And yeah, the almost equality is an equivalence relation. An interesting fact is that you would think it is, but almost containment is not a partial order. And it may be an interesting exercise to come up with why. It's not a partial order. Kind of a funny fact.
You mean it's
Not-
like
What?
it's not transitive.
Yeah, I know.
Or I mean, that's it's not just that it's pre-order.
It's not transitive. Yeah.
Yeah.
Yes, it is not transitive. Okay. Okay, so we're about to stop for this thing. So maybe what I'll do is just state the stationary decomposition theorem, which is what we're going to do. So this is stationary decomposition. And then we'll prove it after the break. So just it's the obvious statement given everything I've said so far. So let x non-empty be definable. Then x is a disjoint union That is not it's the spelling of disjoint. X is 8. Joint union. Say x equals x1 through xn, where each xi is stationary and each dimension of xi is the same as the dimension of x. So given any definable set, we can split it into a finite disjoint union of stationary sets of the same dimension. Moreover, the uniqueness part is the xi are unique up to almost equality. Okay, so every definable set has a unique factorization. It decomposes into stationary components uniquely up to almost equality. So that's where we're going. And we'll stop there for now.
Thanks. Are there any questions?
So what's the relation of between this stationary and the stationary type?
Between stationary and what?
Stationary type.
Oh, stationary type. Well, so every stationary definable set has a generic type, and the generic type is a stationary type. So in abstract stability, you don't have a notion of a stationary definable set. The rough translation of how you get from everything we're doing to abstract stability is that you forget about definable sets and you work mainly with types. And there you have a notion of stationary type, and the stationary type says you can't take two distinct non-forking extensions, and that's the same as saying it doesn't decompose into two equal-sized pieces. We have the benefit that we can do it at the level of definable sets because we're in a strongly minimal structure, and you can't do that in general. So for us, we're just saying the definable set is stationary, but that just means that the generic type is a stationary type. So that's the relation.
Maybe you could say it like, in those cases, stationary means Morley degree 1, if you were in the strongly minimal theory.
Yes, yeah, yeah, okay. Like I said, we're really saying Morley degree stationary is the same as having Morley degree 1. A stationary type is the same as the type having Morley degree 1. So. I'm trying to give a preview of abstract stability at the same time as doing strong minimality, so that this is what stationarity is supposed to mean in abstract stability. It comes from this notion.
Are there any other questions? Well, if not, then we have a half-hour break until, in our time zone, 1:45, which is like 12:45 in the morning where you are, I guess.
Yeah, I can figure out the time. It's okay.
Yeah. Okay. So yeah, we'll resume in a half hour. Wait, what I was trying to say about I don't know if you can hear me. I was trying to say is that relation isn't anti-symmetric either. I think that's what I was saying, that it's not a pre-order because, oh, sorry, turn the recording. Probably. Are you trying to turn off recording? Yeah. I just is it do it or no? Oh, how do we stop it? I mean, we want to pause it, right?
We only pause it.
Oh, sorry, did I screw up?
Cancel.
Okay. How do we pause the recording?
Oh yeah.
Oh, cool. Good. Okay. Now you can get started.
Okay, cool. So picking up, we're just going to prove the stationary decomposition theorem. So again, this is the statement. So you have a non-empty definable set, then you can write it as a disjoint union of stationary sets of the same dimension. And moreover, they're unique up to almost equality. Okay, so the first part of this is an exercise. So part 1 is exercise. I guess is a two-part exercise. So if x is in m to the n and dimension of x is less than n, so it's like a small subset of m to the n, then there exists a finite to 1 definable function from x to m to the n minus 1. And moreover, I should say, you can define f without introducing any new parameters. So to make this precise, I should say this is a definable. So x is in m to the n, it's a definable. Then you can find a finite to 1 a definable function. Okay, so a small set can always be mapped to a smaller power of m. And if I remember correctly, the trick here is to look at a projection to m. So in other words, this is like 1 cutting. So you do this m cutting thing, but you use 1. Right? So you break it into a bunch of subsets of m to the m minus 1, and well, most of those have to be small somehow, and then you can kind of piece those together. Maybe it's supposed to be n minus 1 cutting. I'm not entirely sure. Regardless, I believe it's straightforward to do, and I might be blanking on the which one it is. Okay, B. So you project to either 1 or n minus 1, and use the fact that the dimension is less than n, meaning that like most of the fibers are small. Okay. B is using that conclude that if x is a definable and of any dimension, so of dimension d, then there is a finite to 1 a definable function from x to m to the d. Okay, so a set of dimension d can always be mapped to m to the d with finite fibers. And well, this is just by use a plus induction. Right, so if the dimension, so if you're in m to the n, if you're dimension n, you're done. Right, if you're not dimension n, then you can go down to n minus 1, and from there you use induction. Okay, so that's part 1. And now part 2 is the rest of the proof. So let's do the existence of the decomposition. So the decomposition exists. Okay, well let's take this function. So let f be as above. So let f x to m to the d as above, where d is the dimension of x. I suppose this is where we're using that x is not empty, right? Because it goes to m to the d for an actual value of d. Okay, so by uniform finiteness, so it's a finite to 1 function. By uniform finiteness, the fibers are bounded by something. So uniform finiteness. I think this is another exercise I failed to state yesterday. We did uniform finiteness in M, but it also holds in any power of M. Okay, so uniform finiteness, there exists some, let's say K, such that each fiber has size at most K. Okay, so what we've done is we've said because the set has dimension D, we can view it as something like a K cover of M to the D. That's the picture. Right. So now claim, what does that do for us? That's going to tell us a bound on how many stationary pieces we could decompose into. So since this function is K to 1, what that's going to tell us is we have at most k many things we could decompose into. So precisely the way we'll say it is that there is no decomposition of X as a disjoint union of up to k plus 1. So you cannot split X into k plus 1 sets of the same dimension. Okay, and this is really all we need. So we want to show, look, where are we going? We want to show you can decompose into irreducible pieces. The way you do that is you take a maximal decomposition. Well, you need to know that there is a maximal decomposition in the first place, and the way you do that is you say that there's a bound on how far a decomposition could possibly go, and then because there's a bound, you can go as like the furthest you can go within the bound is a well-defined thing. So that's why we need this. So there is no decomposition up to k plus 1 pieces. Why is that? Well, suppose there was. If so, now we use our basic facts about dimension. So each f of xi has dimension d. Because f is finite to 1 and dimension is preserved under finite to finite correspondences. So because this function f is finite to 1, it's going to send d-dimensional sets to d-dimensional sets. In particular, each of the xi's goes to something of dimension d. Okay, well now m to the d is stationary. So these f of xi's belong to the unique generic type of m to the d. So in other words, stationary means there's a unique generic type, meaning, well, if you take all of the d-dimensional subsets of m to the d, they form a type. They're closed. It's closed under conjunctions, right? In particular, the intersection of all of the f of xi's also belongs to the generic type. This is also in the generic type. And in particular, the intersection is non-empty. Right, so I'm just saying that because m to the d is stationary, if you take a whole bunch of d-dimensional subsets, but finitely many, and you intersect them, it has to be non-empty. Okay. This is actually an exercise as well. I think I wrote this as an exercise. If you take a stationary set, then any two definable subsets of the same dimension have non-empty intersection, any finite number. Okay. Well, now let's take a point. So let y be in the intersection of f of xi. Okay, and well, we're done. So then if we look at f inverse of y, it has a point in each xi. Which means that the size of f inverse of y is at least k plus 1, and that can't happen. Because all the fibers have size at most k. Okay, so that's really where we get the stationary decomposition from. It's out of this. Any definable set is like a finite cover of m to its dimension. Okay, so now using the claim, so by the claim, we can take a maximal decomposition of X into disjoint dim X dimensional subsets. Okay, so a maximal splitting into definable subsets of the same dimension. Why is there maximal splitting? Well, you just keep splitting. If it's already stationary, you're done. If it's not, split it into two, continue. After k plus 1 steps, you have to be done. Or after k steps. Okay, and just by definition, so by the maximality, these subsets have to be stationary. Because if they weren't, then you could refine them further and you would get a bigger decomposition. Okay, so that's it. So it's really it's sort of the obvious proof of existence of a factorization into irreducible pieces. You factor over and over again, and then at some point you stop. The point is we needed to know that you couldn't keep factoring forever, and that's because of this k-to-1, this finite to one definable function with the uniform finiteness. Okay, so that's part 2, and now part 3 is the uniqueness. This should be fairly straightforward, I think. So suppose we have 2 decompositions. So x is x1. I should find this in the notes and make sure I'm doing the same thing. Yeah, right. x1 through xm, and it's also equal to y1 through yk. Okay, so suppose we have 2 such decompositions. The goal is to say that each of the xi's is almost equal to one of the y's, and similarly, each of the y's is almost equal to one of the xi's. Okay, so let's just, it's a symmetric argument, so we'll just do the one direction. So fix any xi. Okay. Well, then xi is contained in the union of the y's. Because it's contained in x. And so you can write xi as the union, the disjoint union over all the j. Okay, this is a disjoint union over all the j of the yj part of xi, right? So you can split xi into pieces according to the y decomposition, and because xi is stationary, there is a unique j so that has the same dimension. So there is a unique j where dimension of xi intersect yj is the same. Okay. Well, I suppose this is another exercise. That just means that xi and yj are almost equal. So in other words, if you have 2 stationary sets, they have the same dimension, and their intersection also has that same dimension, they have to be almost equal. And that's another one of the exercises. Okay, not too hard, I think. So you decompose, xi into its yj part and its not yj part, I believe it is how you get that. And the idea is that by stationarity, the non-yj part has to be small. And that means that xi is almost contained in yj, and then the reverse also holds. All right, so that's it. So that's the existence uniqueness of the stationary decomposition. And this leads to the definition of what we'll call the degree. This is the, if you know what this is the Morley degree. So the degree of x is just the number of xi's, and the xi's themselves are called stationary components. That's what I'll call them. So it's like irreducible components, except they're called stationary. Okay, so the stationary components are well defined, but only up to almost equality. All right. Right, so there's a prettier way of saying all this, which sort of foreshadows how this works in more general stability, which is that instead of doing this up to almost equality, why don't we just replace the definable sets themselves with almost equality classes. So more something aesthetically pleasingly. I won't write that out. Alternatively, consider almost equality classes, and this is a big preview of where we're going, so this is an important notion. Consider almost equality classes which I'll denote, like that. It's like the class of X of stationary definable sets. Actually, no, just of definable sets. Okay. Then each class will factor exactly uniquely. So each class factors uniquely into stationary classes. A union of stationary classes, which you can then also call the stationary components of the original class. So everything I just said, has to be made sense of. You have to check that all of that is well defined and that it's like a reasonable thing to state that makes sense. And doing that is another exercise. So make sense of that. Okay. And the last thing I was going to say, this is a kind of neat fact that comes out of this. So maybe you're familiar with the notion of isolated types, atomic models, etc. So recall, this is not really that important, but it'll come up once or twice later, and it just comes out of the stationary decomposition. So recall, a type is isolated. P is isolated if it's implied by a single formula in P. So if it's implied entirely by one formula. Okay, and well, isolated types are quite important in omega stability, and therefore in strong minimality, they let you construct things called prime models, which are like the smallest models of a theory. You build them by realizing a bunch of isolated types. There's a sense in which, in a strongly minimal theory, you kind of want to. So an Aleph zero categorical theory is one where every single type is isolated, no matter what. In an omega stable theory, and in particular strongly minimal theory, you don't get that every type is isolated, but you almost do. You get that every type is almost isolated. So here's an exercise. So say let P be, say, an n type over A. So P is a complete n type over A. Then P is almost isolated. What do I mean by almost isolated? So there is going to be some formula in P so that every other formula is almost implied by P. So such that for all other formulas psi in P, phi is almost contained in psi. Okay, so this is something that we use. So it's sort of saying every type is the generic type of one definable set. So you can identify the type with one definable set. And so there's a correspondence somehow between types and certain definable sets. Okay. A corollary of this, if you really want to do it this way, a corollary of this is that strong minimality implies omega stability, but that's kind of a silly way of doing it. You can do that more directly. Okay, so now let's recap. So what I want to do now is something a bit sketchy. So what we're going to do is recap everything we've done. So just rewrite, this is everything we've done. This is dimension. It's great. We're kind of done with just dimension of definable sets. Then we're going to move to interpretable sets. And I'm hoping to convince you that if you move to interpretable sets, everything still works. But I'm not going to do all the same stuff. I'm not going to do all the details. I'm just going to say, here is the trick for why everything still works. And trust me and do it as an exercise, everything still works. Okay, so that's the goal. So in order to successfully do that, we're going to have a recap theorem. So recap, this is like abstract properties of dimension. So I'm trying to preview all the properties of dimension that could adapt to interpretable sets. So an example of a property of dimension that we don't want to care about right now is that the dimension of m to the n is n, right? But like the more abstract things. So this is a whole bunch of stuff. This is like what we've proved so far. So dimension is definable. The characterization, so dimension of x equals negative infinity if and only if x is empty, and then 0 if and only if it's finite and not empty. Okay, the union theorem, so the union lemma. Recall the union lemma says that if x is a subset of y, then the dimension of x is at most a dimension of y. And the dimension of a finite union is just the max of the pieces. Okay. Function additivity. And this is the one where you say you can compute the dimension of the domain of a function by breaking it into the dimensions of the codomain with the fibers on top. So it's the max value of the I plus the dimension of the people that have I-sized fibers. Okay, invariance. So dimension is invariant under finite to finite correspondences. Products behave nicely, although I don't think I really have to add. Some of this stuff it like falls out. Some of these are dependent. Right? Products and stationary decomposition. So the stationary decomposition theorem. So this is like my summary of here's properties of dimension. So it's definable. You have the nice characterizations of when it's negative infinity and 0. You have it behaves well with respect to subsets and unions. It has the additivity property. It's invariant under finite to finite correspondences. It respects products, and it has the stationary decomposition theorem. Okay, so stationary decompositions exist and they're unique. I know that's a lot. I'm just sort of reviewing. This is the list that I want to rewrite again. Now that we've done that, I'm going to end section 3 and now go on to section 4, which is interpretable sets. Okay, why are we doing this? So our goal is to interpret a group. The main theorem of the course is interpret a group in certain structures. Show that certain structures have groups. It's going to have to be an interpretable group, not a definable group. We're going to have to mod by an equivalence relation to get it. And well, if you want to do that and you want to have all the same machinery that we're developing, then you need to know the dimension theory goes through after modding by an equivalence relation. And this is a bit annoying. So we're going to do that. And I'm just going to say, here's what interpretable sets are. Here's the one trick you need. And now you can do it. Okay. So to start with interpretable sets, we'll just review. So first, we'll just review what that is. And to streamline it, I am going to review the thing called MEQ. It's just the most convenient way of doing this. So review MEQ is the first goal. So remember, here's what MEQ is. I don't know if you've seen MEQ before, but here's what it is. So this works for any structure M. So for any structure M, you can pretend that it's still strongly minimal if you want. So we define a, oh, by the way, I should just say, what are interpretable sets? Okay, an interpretable set. So remember, interpretable set. What that means is you take a definable set, mod a definable equivalence relation. That's literally what I mean by that. If you haven't seen that before, that's just what it means. Definable set, mod a definable equivalence relation. MEQ is a different structure attached to M, which captures all the interpretable sets. It makes the interpretable sets definable. Okay, so we define a multi-sorted, I guess I can call this an official definition, structure MEQ. Okay, I'm not going to review multi-sorted. At least my plan is to not, but you can, I mean, like, tell me if I should. If the organizers think I should, I can.
I feel like it's kind of a pain to review
Yeah.
it.
It is a pain.
Maybe let's not.
Okay.
So we really review multi-sorted structures. Okay, let's not.
Okay, I mean a multi-sorted structure. So rough the 1 minute version is you have, instead of just a single type of element, you have sorts, and every element comes with a sort. So think like the canonical example is like you have a two-sorted language of vector spaces where you have a sort for scalars from the field, and then you have a sort for vectors from the vector space. And then everything in the language in a multi-sorted structure comes with, instead of just being like an n-ary function or an n-ary relation, it comes with sorts it goes with. So like in a vector in a field with a vector space, you have like field multiplication, which is multiplication in that particular sort. And then you have like scaling, which is field scale, which is like scalar vector multiplication. So scaling only makes sense for the scalar and a vector, right? So every relation comes with prefix sorts, and then you sort of do that, and everything works. So that's a horrible way of, but that's sure. That's what multi-sorted logic is. So we define MEQ, and the way it works. So the sorts. So there is a sort for each zero interpretable set. Okay, a zero interpretable set, meaning, well, do I even want to say it that way? I won't say it that way. Okay, I'm going to do even fewer sorts than that. So we have one sort for each zero definable equivalence relation on each m to the n. So for each n, if you have a zero definable, so definable without parameters, equivalence relation on m to the n, then you put a sort into the language corresponding to that equivalence relation. I'll call the relation E, and the sort is going to be for the elements of m to the n mod E. So you have a sort for m to the n mod E for each E, and then the language is, well, you have the original language on M, language on M, which if we're being very careful about this, M is m to the 1 mod equality. Like if you really want, you don't have to include M, you can just take the quotients by equivalence relations and you already have M. Plus the projection maps. Okay, so what does that mean if F refines E? So if you have two equivalence relations on m to the n and F refines E, then you have a projection going from Am I writing in the right direction? No, I'm not. F first, right? The quotient by F to the quotient by E. Okay. You don't even have to do that. You can just take the projection from M to the N to M to the N mod E, and you get the same thing. Okay. And so that's the structure MEQ. And well, so the point is that now interpretable sets, so exercise, every interpretable set in M is definable in a canonical way. There's a way of viewing it as a definable set in MEQ. Okay, so if you want to think about interpretable sets, you can call them definable as long as you're working in this other structure, MEQ. And part of the exercise is that this actually works over parameters. So precisely, if let's say X is a definable in M to the N, and E is a definable, an equivalence relation on X, then the quotient X mod E is in a canonical way, you can view it as some a definable set in MEQ. Okay, it's not literally a set in MEQ, but you can canonically identify it with a set in MEQ. Okay, that's an exercise. So what am I saying here is that the equivalence relation E doesn't correspond to one of the sorts because E is just a definable, it's not zero definable. So the reason that you only mod out by zero definable relations when you define MEQ is that you want there to be a theory. You want there to be a theory TEQ, which corresponds to T. And in order to do that, you can't add parameters anywhere you want when you define the sorts, right? The sorts have to be entirely determined by the theory T. So you only do the things that are defined without parameters, but then what I'm saying is you still get the interpretable sets over parameters. And the way you do it is you just have to sort of define a bigger set with a bigger equivalence relation. And then realize this is like a fiber in that. Okay? So, but the point, MEQ is a very convenient way of viewing all interpretable sets as definable, and every A interpretable set is now A definable in MEQ. Okay, so caution, MEQ is not a strongly minimal structure, really. I mean, it doesn't really make sense anymore. Is not strongly minimal because strongly minimal is only for one-sorted structures. It's a one-sorted definition. But you can still talk about definable sets being strongly minimal. And, well, the definable set M is strongly minimal in MEQ. So it's like still somehow strongly minimal. Okay. I don't really want to go through all of this, but the general thing is that when you pass to MEQ, you don't really change much, right? So passing to MEQ is typically harmless. And well, I'll just say out loud, there's an exercise, so see exercise. So like, you know, if you have a complete theory T, then you get a complete theory TEQ, which is just the complete theory of any model of T expanded to its EQ. And passing to MEQ doesn't change the definable sets. So in particular, I'll say in particular, the zero definable subsets of M to the N are the same in M and MEQ. And moreover, just the interpretable sets in M are the same as the interpretable sets in MEQ. So we have not introduced new definable sets. We've just taken interpretable sets and called them definable. And that's it. Okay. It's just a convenient way of packaging the collection of interpretable sets. So from now on, so I'm gonna like work in MEQ now. So now we work in MEQ. And the goal is transfer dimension theory. From M to MEQ. Okay, which it sounds like a mess, right? It sounds like, oh, you've got all these equivalence relations and we have to do a whole bunch of more cases and stuff to like to say what the dimension of a quotient is going to be, but really there's just one trick and it makes it much easier. So I'll just say like a strategy that you could use to do this is you could define Morley rank. You could do everything that we've done much more abstractly by doing Morley rank. And then you could just show that MEQ is still omega stable, so it still has Morley rank, and then you already have your definition. But well, there's something more like visceral that we can do, which I think is kind of nicer. So here's what we're going to do. So how? Using what I'll call approximate definable choice. Which is also called weak elimination of imaginaries. So elimination of imaginaries is a notion that says MEQ is the same as M. Basically, it means that if when you expand to MEQ, like you don't gain anything because all the interpretable sets were already identifiable as definable sets. Weak elimination of imaginaries is like close, but not quite the same. And it turns out that strongly minimal structures already have weak elimination of imaginaries, which means, roughly speaking, the interpretable sets can be very nearly identified as definable sets already before we start. And so you don't even have to do anything. You just kind of say, given an interpretable set, it's like very close to some definable set, and then you just define it, the dimension to agree with that definable set. Okay, so what do these things say? So definable choice would say, if you have a collection of non-empty sets, which is a definable collection, then there is a choice function which picks one element for each of them, and the choice function is also definable. That would be a definable choice. Definable approximate choice is going to allow picking not one, but finitely many per set. Okay, so let's get into it. So lemma, this is approximate definable choice. So let's say that I'm working in MEQ now, but so definable now means definable in MEQ. But if I want to say definable in the original M, I'll just say that it's contained in M to the N. Okay, so let X in M to the N times T, definable now in MEQ. And assume that for all T and T, the fiber XT is non-empty. Okay, so I'm like setting up the axiom of choice. I have a collection of non-empty sets, and it's a definable collection. Then there is some subset Y definable, which is picking a finite subset of each of the XTs. So that each YT is non-empty finite. Okay, now there's one really unfortunate feature of this, which is that this you can't do there's like in most things where we have from some definable thing we get another definable thing, you like it to be uniform. So if the first thing was definable over some parameter set, then so is the second. That fails here. So we need, in general, we need extra parameters to define Y. So this is very unfortunate. And it messes with things a little bit. But it will be okay. Okay, so proof. So this is induct on n, of course. Okay, if n equals 0, then there's nothing to say. This is a trivial statement because then all the xt's are just a single point and they're already finite. Great. So the n equals 1 and n equals bigger than 1 cases are roughly the same difficulty. So the inductive step is going to be conceptually clear, but it's a little bit annoying to write down. The n equals 1 case is where the argument really happens, though. So here's the argument for n equals 1. So by uniform finiteness, we can fix some, what do I call it? N, fix n, sorry, bad spelling. So that for all t, one of two things happens, either xt is at most n or the complement is at most n. So it's a definable family, so uniform finiteness gives an n that says finite means at most n, cofinite means everything but n. Okay. Now there's a very nice trick, which is that we just fix more than that. So fix, say, a n plus 1 distinct points. And these are the extra parameters that we need. So I said we need extra parameters, it's these things. And now we define yt equals, I guess I'll have to skip to the next page, it's one of two things. So by strong minimality, xt is finite or cofinite. So it's either xt if xt is finite, because again, we're trying to choose a finite subset of xt. If xt is finite, we already have one. What if xt is cofinite? Well, then we're going to intersect it with these parameters if it's cofinite. You see how that works? So since we have since xt is cofinite, it contains all but n points. And so if we take n plus 1 points, one of them has to be in xt. So the point being one of our n plus 1 points is in xt by the choice of n. So this is a non-empty finite set. Okay, and that's a definable form. I just gave a formula for how to define yt. It's definable, so you get this definable family y. Okay. Right. So now what about n plus 1? How do we do the n plus 1 case? Well, maybe I can, because I said I want to save some time, maybe I can just sketch how to do it and then you can fill in the details, because I think the sketch is probably clear enough. So we have xt in m to the n times m for all t. Okay. And xt is non-empty, so what we do is we just look at all of the m to the n coordinates of points in xt. We pick a finite set of those, and then for each one, we pick a finite set of extensions to m to the n plus 1. Okay, so each pi of xt, so this is the projection inside m to the n, is non-empty. Because xt is non-empty, it has to project somewhere. So we can choose first a non-empty finite subset which maybe we'll call zt inside of pi of xt. And this is uniformly definably, whatever you want to say. So definably in T, we can choose the set ZT, which is in the projection to m to the n. Why? This is the inductive step. So okay, this is induction. This is we're inducting. So great. So now we have ZT, which is a finite set of coordinates in m to the n. So each z in ZT extends to xt by some non-empty set of points in M. So if I have one of these ZTs, I know it extends to a point in xt, and that means that what that means is there's a last coordinate that you can add. Now you take the set of all of the last coordinates that you can add, and that's a non-empty set, and now we choose a finite subset of that. So choose a non-empty finite subset. Maybe we'll say WT. This is now contained in M. And now, I'm sorry, it's not WT because now it depends. So WTZ. Okay, so Z is in ZT, then corresponding to T and Z, we have a finite set of extensions and we pick a finitely many. Okay, so, and now take finally our set YT that we've wanted to choose this whole time is the set of all WZ. I actually think it's ZW, whatever, where Z is in ZT and W is in WZT. Okay, and that's the sketch, and I'm hoping that if you want, you can turn that into a proof. So it's just saying, you know, you project to one coordinate less, you choose a finite set there, and then you extend that to the original coordinates in a finite set of ways. And so the real argument happens just in the n equals 1 case. Okay, so why is this great? This is beautiful. This just makes our interpretable sets work. So corollary, weak elimination of imaginaries. Yeah, imaginaries. Let's let x be any, or did I say that? Wait, I say y. I said okay. So let y in m to the n mod e be definable in MEQ. Okay, so we know that y is a quotient of some subset of m to the n, right? In particular, it's a quotient of its preimage. So you can write y as the image of its preimage under the quotient map, but you can do better. So the weak elimination of imaginaries says there is some x in m to the n definable so that the projection of x equals y. And by that, what I really mean is x mod e is y. Okay, so the points in x project exactly to y when you mod by e. And this projection x to y is finite to 1. Okay, so in other words, so the slogan, again, I like slogans for theorems. So the slogan is that every interpretable set is a finite to 1 image of a definable set. And again, it's kind of funny that the set x and the function, they're defined over additional parameters. You can't control what parameters define them, but you know that they're there. So there is some definable set that covers y in a finite to 1 way. Okay, so now we're done. So now we just say if y is MEQ definable, so it's interpretable, we set dimension of y to be dimension of x for any x as above. Okay, and now I'm done with my part, and then you do the rest, right? So, exercises about this. So check that makes sense. So exercises, this is well defined. Okay, I think that's clear. If you choose two different definable sets and they both project finite to 1 to x to y, then those two definable sets are in a finite to finite correspondence witnessed by y. And so they have the same dimension. Okay. Oh, did I not prove this? I didn't prove. Oh, I wrote down corollary and then I didn't prove it. Is the proof clear? The proof is one line. So we can, given any family of non-empty sets, we can choose a finite subset uniformly of each one. So do that. So y is the image of x. And so you take all the equivalence classes in X and you pick a finite subset. Okay, you write, okay, I'm sorry. I didn't prove that. So first, proof. Okay, proof of corollary before the exercises. Proof of corollary is simply the following. So proof of the corollary. Write y first as z mod e, where z is definable in m to the n, and then choose a finite non-empty subset of each class in Z.
So Z is functioning as the T in the theorem. I mean, in the
No, y is the T.
Oh yeah, sorry. Y is the set
Yeah.
T. It's essential that that set T is interpretable, not just definable.
It doesn't matter. The approximate choice thing, I assumed that the set was interpretable.
Yeah. And saying like it's important that in that lemma, T was allowed to be interpretable, not just definable.
Yeah. It was. So yeah. Okay, so yeah, y is a collection of sets. Y is a collection of equivalence classes, and just pick a finite subset of each one. Okay, so now the exercises. Okay, well, the first obvious exercise is that dimension of y is well defined. And the second, much less obvious exercise, which I'm kind of cheating significantly here, but all of our abstract properties of dimension still hold. Okay, so what do I mean? This is why I wrote these down. So it's like 1 through 7. Where were they? Wow, that was a while ago. Okay, here are these 1 through 7. Okay, these will still hold in MEQ. So the dimension is still definable. You still get, for example, why is the dimension 0 still the same as being finite? Well, it's because, if y is interpretable, then y having dimension 0 means that it's in finite correspondence with a finite set, and that means it's finite, right? Etc. So all of these things are going to be still true. And in particular, you can define stationary in exactly the same way. So a stationary set is one that can't be decomposed into two sets of the same dimension. And then you still get the decomposition of any definable set in MEQ into stationary components. It's still unique up to almost equality. Okay. And roughly speaking, prove this by just transferring two to m to the n. Okay. Now there's two ways you could transfer to m to the n. One way would be you just take the finite cover. So every interpretable set has a finite cover in m to the n. In some of these, that's the way to do it. So you just directly transfer to the same statement in m to the n. In some of these, that's not the way to do it, because in some of these, it's more helpful to take just the preimage of y literally under the quotient map from the sort that it comes from. And so it's sort of, I guess, your job to work that out. And in particular, the most complicated, I believe the most complicated is checking that dimension is still definable. And it's frustrating. The reason that that's complicated is that if you use the weak elimination of imaginaries, you have to worry about the extra parameters. That only works over extra parameters, and to check the dimension is definable, you can't add parameters. So you just can't use that there. So again, I know that this is a big, like, I'm ignoring a whole bunch, but in the sake of time, that's really what we need to do. Let's just say dimension theory works in MEQ. And it's not crazy to check. Okay. So if it's okay, I'm just going to go on. So that was section 4. Okay. That was just section 4 of the class. Now we go to section 5. So sections 6 and 7 are the big dense sections. So I want to, the goal was really to spend almost all of tomorrow on number 6 and then almost all of Thursday on number 7. So I want to get through section 5 as much as possible, but I don't want to rush through it. So it's good to start it today is what I'm saying. So section 5 is dimension of types. So I said yesterday that lots of sources will define dimension of types first and then use that to define the dimension of a set. And that I wanted to do it backwards by doing sets first, then types. So now we're going to do that, right? So now we go from sets to types. And what we're going to do is like, okay, well, really, practically speaking, we have a whole new dimension theory. So we have our dimension theory we did, and now we're going to have a different dimension theory. But it's really not different. It's like they're linked in a clear way. And it's like, it's useful to have both of them, right? We'll use both of them. Okay. So goal is to define the following notation. Goal is to define dim A over A. Okay. So here A is going to be a tuple from MEQ. So it's, a finite tuple from MEQ, and A is just a small, just a subset of MEQ. Okay. And this really means, so I said dimension of types. It really means dimension of the type of A over A, little a over big A. Okay, so the type of little a over big A just means all the formulas of little a that are true with parameters from big A. And so we're going to define the dimension of that type. But we're going to denote it usually as dim of little a over big A just for convenience. It's like more annoying to write the type part every time. But in particular, if 2 points have the same type, they're going to end up having the same dimension. So it's well defined to do that. Okay. For this to be meaningful, so for this to be, well, meaningful, I say, in order for that notion of dimension to really capture everything we want it to capture, we no longer want to just work in any model. So we have to work in the right model. And so the first goal is we have to talk about what saturated models are. So I don't exactly, I'm assuming that maybe some of you have seen this, maybe some of you haven't. So I'm going to quickly review what a saturated model is, the basic facts about them. So what is a saturated model? So definition, so M is saturated And this makes sense for any infinite structure. It doesn't have to be strongly minimal. So an infinite structure, I suppose you could define it for a finite structure, but I haven't thought about whether that looks weird. So an infinite structure M is saturated if you can realize the most number of types that you possibly could inside M. So if for all A subset of M, where A is smaller than M, every type over A is realized in M. Okay, so you, in other words, take any small set, any set which is smaller than M, and add all of those to the language as constants, and then take any complete theory there. There is a take any type in that expanded language, you can find a realization of that in M. So it's sort of saying the compactness theorem holds inside the model M, but well, that only is possible to arrange if you just consider like small instances of compactness, so less than size of M. Okay, in this case, so if M is saturated, just to be formal about this, in this case, we literally use the word small. So A is small if the size is less than M. Okay, so saturation means you can realize types over small sets. That's what it means. Okay. Oops. So some basic facts. So two key facts about saturated models. For us, we're going to need this first one. So M is saturated if and only if MEQ is. Okay, so we want to check that most strongly minimal structures are saturated, and well, we need that they're saturated in the EQ version of saturation, but that's automatic. And then the other thing is uniqueness. So uniqueness, if M and N are saturated, elementary equivalent, which I'll denote like that, and have the same cardinality, then they're isomorphic. So saturated model of a theory is unique in its cardinality if it exists. This is back and forth. So if you know the back and forth method, it's just you line up all the elements of the two structures and then you build an isomorphism step by step, going back and forth. The idea is like each point, you have to match it to something in the other structure. Well, the type of that point is realized in the other structure, so you just match it to a realization of the same type. Okay. Now let's check. Strongly minimal structures have a very unique property. The unique property is that almost every model is saturated. That's usually not true, but for strongly minimal structures it is. So lemma, if M is strongly minimal, then to be saturated, you only need to check a little bit, right? So let's say it's uncountable and bigger than the language, bigger than the language. So if we're only considering countable languages, then just has to be uncountable. Then M is saturated. Okay, so normally in model theory, what you do is you start by taking a big saturated model and then you work in that model. You don't really have to do that for us. You just take any uncountable model and that'll do. So let's sketch a proof. Okay, so we let P be an N type over A, where A is small. Okay, we want to show that P is realized in M. we may assume that n equals 1. Because if you can realize any one type over a small set, then to realize an n type, you realize a sequence of one types. So you realize the first coordinate, then once you do that, you put that into the parameter set A, and then you realize the second coordinate, then you put that into the parameter set A, and etc. So by an induction argument. Okay. Now we have two cases. So assume n equals 1, so we have a one type. Now we use strong minimality. So what do the one types look like under strong minimality? So we have two cases. Okay, case 1. Some formula in P has a finite solution set. So every formula in P is either finite or cofinite. Some formula in P is finite. Meaning that's bad wording. It means that it defines a finite set. Okay, in that case, it makes sense to do the following. So choose some phi in P with minimal solution set. So because you have some formula with a finite number of solutions, then you just choose one with the smallest possible number of solutions. Okay. Then it follows that P is isolated by phi. Meaning like any realization of phi, any solution of phi models P. And because phi is a formula and it's a consistent formula, it has to have some solution in the model. So this gives that you have a realization. Okay, which is enough. Why does it follow? So why is this true? Well, if you take any other formula, so for any psi in P, the conjunction is going to imply phi, so it's smaller. So the conjunction is smaller. But it can't be smaller because phi is minimal, so it's actually equivalent. And well, what does that mean? So if phi and psi is equivalent to phi, okay, this is your logic students, you can work this out. What does this means? This is the same thing as this, right? Okay. Yeah. Okay, so that's case 1. That's you have a finite thing. Then it's just saying, well, if there's a finite formula, the type is isolated. Okay. Case 2, not that. Every formula in P is cofinite. Well, now we use that the set is small. Okay, so the solution set of P, so the set of all realizations of the type P is the intersection of now less than m many cofinite sets. Which means it is still cofinite. And in particular, non-empty. Okay, so because the set A is small, there's like not that many cofinite sets that are definable over A. And then you just conjunct all of them. And because M is bigger than that, M still has some solutions. Okay. Now this implies, so corollary of this is that strongly minimal implies, so I mean, we don't really need this, but it's nice to know strongly minimal implies uncountably categorical. So in the beginning, yesterday, when I was talking about Morley's theorem, like you can view uncountably categorical theories as captured by strongly minimal theories. Well, there's one direction of that. So strongly minimal implies uncountably categorical, because, well, saturated models are unique. So if any two big enough models of the same size are isomorphic, in particular, so, okay, in accountable language. Okay, accountable language, I should say. So a strongly minimal theory in accountable language is uncountably categorical, because if any two uncountable models are isomorphic, are saturated, and any two saturated models of the same size are isomorphic, then putting those together, any two uncountable models of the same size are isomorphic. Okay, I know we're wrapping up. So that's the review of saturated models. So we're done with saturated models. So now let's define this notation dim of A over A, which is really the dimension of the type. Okay, so it's straightforward. I give you some like spiel. There's like I said we're gonna do it like 10 minutes ago and I didn't do it. And I could have done it in 5 seconds. So now we'll actually do it. It's not like this some big complicated thing. There's no big surprise here. So it's just dim A over A equals the smallest value of dim X, where X is A definable and A is an X. Okay. So you just look at all the formulas in the type A over A, and you pick one with smallest dimension. And that's supposed to make sense because, well, that is, if we set P to be the type of A over A, then we can write P as just a huge intersection. So it's an intersection over all phi in the type of, phi of the set of solutions. Okay, and then what we're saying is that the dimension of P is just this here is a filtered intersection, meaning it's an intersection of a collection of sets. It's closed under finite intersection. It's just the smallest dimension of phi of M appearing there. Yeah. Okay. I think no, let's just stop because I think that everything else is going to be too complicated to do. But so we'll stop there.
All right. So are there any questions? If not, we can thank Ben for today's lectures and when the section is what, 6:30? Is that right? Okay, in this room, and yeah, we'll see Ben tomorrow. So I guess that's everything.
Okay, great. Yeah, see you tomorrow.
Oh, yeah. Well, it's the stop button here. Especially when you're doing a lot of recording like this. So you're hearing now. Yeah, it's funny. Oh, sorry. Okay. Oh, I said, yeah. Oh, my bad. I thought that. Yeah.